Hey everyone, here are some notes on solution stoichiometry. We're going to use our knowledge of the mole, stoichiometry, and solutions to solve these problems. We may use Appendix A2, which are the solubility rules, A1, and the periodic table of elements will help you write formulas properly, so have those available. And then we're going to apply concentration stoichiometry to solve the problems. The general setup for solution stoichiometry or solving concentration stoichiometry problems is as follows. It's a mole map, except we start with volume in liters and we use molarity to cancel the liters. So this molarity is our new stoichiometric factor or conversion factor. So this is our new conversion factor. And the units are moles in 1 liter, where in this case the liter, which is a measurement for volume, liter gets the 1. So we can use molarity to convert volume to moles. Moles of what? Moles of A. For moles of A, we can use the mole ratio to convert to moles of B, and for moles of B, we can use molar mass of that new substance to determine the grams of B. Tips for success. First, you want to write a balanced equation, and perhaps it's a double replacement equation where you have to predict the products and then go back and add coefficients to balance them. From there, we'll calculate the amount of substance B from 2 given quantities. Then we'll identify the limiting reactant. So we'll look at the reactants, we'll decide which one is limiting how much product can be produced. And from there, we'll identify the excess reactant and determine the amount of excess reactant that remains. Here's an example of a problem. We're going to use concentration stoichiometry to convert quantities. What mass of silver chloride will be produced when 4.25 grams of silver nitrate reacts with 25.0 milliliters of 0.0330 molarity or molar concentration of barium chloride solution? So the first thing you might want to do is write the word equation before you go ahead and balance it. So the word equation is we have silver nitrate and we have it reacting with barium chloride. So those are reactants. So silver nitrate aqueous plus barium chloride aqueous yields, this is a double replacement reaction, so the cations switch places, so yields silver chloride solid. We can use our solubility rules to determine that silver chloride is insoluble plus barium nitrate. And if you remember from our solubility rules, all nitrates are soluble, so it remain aqueous or in solution. Okay. So that's our word equation. From the word equation, we can write a balanced molecular equation. So silver, Ag nitrate, NO3, aqueous, reacts with barium chloride, aqueous. Feel free to use Appendix 1 in the periodic table to determine how you're going to write these molecular formulas properly. Yields Ag Cl solid, because it's insoluble, plus BaNO3 to aqueous. Okay, now we can go ahead and balance the molecular equation using our coefficients. 1 Ag, 1 Ag, 1 NO3, 2 NO3, so we'll put a 2 there. Changing that to 2 Ags, and changing the Cl's to 2, and therefore we are balanced. So our coefficients are 2 to 1 to 2 to understood 1. Okay. So now we want to calculate this mass of silver chloride that will be produced theoretically and identify which of the reactants, AgNO3 or BaCl2, is limiting how much AgCl that can be produced. Okay. So from the equation, we have two quantities we need to convert. We need to convert the grams of silver nitrate, or the mass of silver nitrate. This will be one of our A's substances. And we have to convert it to the mass of silver chloride here, the mass of silver chloride. So this is going to be our B substance, our product. We have another quantity here, barium chloride, 25.0 milliliters of barium chloride, that needs to be converted. And so this is going to be our other A substance. So we have two A quantities we're going to convert. So let's start with the first one. So if we have 4.25 grams of silver nitrate, AgNO3, this was given in the balanced equation. So we'll start there. And we want to convert to grams of AgCl. So we're going to use our mole math. So the mass of A and 1 mole of AgNO3, there are 169.91 grams of AgNO3. That's the molar mass. And then we use the mole ratio to calculate how many moles, to get the moles of A to cancel. So we can calculate the moles of B, which is AgCl. From the balanced equation, we can see that for every 2 moles of AgCl that get produced, 2 moles of AgNO3 must react. So it's a 2 to 2 ratio. And we're going to use the molar mass of the new substance, B, AgCl. So in 1 mole of AgCl, we're going to use the molar mass to convert quantities. So the molar mass of AgCl is 143.35 grams in a mole of it. So when we plug this into our calculator, we end up with a calculator number 3.5856 ... And we want to round it to 3 sig figs. So 3 sig figs, look to the right, so it's about 3.59 grams of AgCl are produced when we start with 4.25 grams of AgNO3. Okay, but we have another quantity we need to convert, and that's the BaCl2. So according to the problem, we start with a volume of 25.0 milliliters of barium chloride. And recall that the general setup is start with the volume and use molarity as a conversion factor. So we're going to do that. So we're going to start with 25.0 milliliters milliliters of BaCl2 over 1. We need to convert it to liters so we can use molarity as our conversion factor and cancel the liters eventually. So we know that in 1 liter of BaCl2 there is 1,000 milliliters of BaCl2. So we can go ahead and cancel the milliliters. Now we have liters, so that's the volume of BaCl2 solution, and we know from the molarity from the problem that, because remember that big M equals moles per liter. So in 1 liter of BaCl2 there are 0.0330 moles. 0.0330 moles of BaCl2. And we can cancel liters. So now we have moles of BaCl2, but we want to get mass of AgCl. So we've got to use the mole ratio. So moles of BaCl2 to moles of AgCl. And from the balanced equation, we can see that for every 1 mole of BaCl2 that reacts, 2 moles of AgCl are produced. And so now we've got to use the molar mass, 1 mole of AgCl. In 1 mole of AgCl, there's 143.35 grams of AgCl, so that the moles cancel, and we end up with, if you take this is AgCl, and if you take the product of the numerator divided by the product of the denominator, the calculator number is 0.236528, rounded to 3 sig figs from the original measurement, and we can round that to about 0.237 grams of AgCl. So when comparing these two quantities, okay, which of the reactants produce the least amount of product? Because that's our limiting reactant. Well, comparing AgCl, which is our product, BaCl2 produced the least amount. So that's our limiting reactant. So this ends up being how much product gets, the mass of the product. So the limiting reactant is BaCl2. The excess reactant is AgNO3. And the mass of the product is 0.237 grams of AgCl. That's the mass of the product that forms. So now we're going to determine the mass of the excess, which is AgNO3. So here we're going to determine the mass of the excess remaining. So remember that the excess was identified as AgNO3. And we know that the mass of the product, substance A, is 0.237 grams, so substance A is AgCl. So we want to convert this product, this amount of product, to the mass of the excess, so we can calculate the excess remaining. So we start with the mass of the product, which is 0.237 grams of AgCl. And we're going to use our mole map. And so in 1 mole of AgCl, the molar mass is 143.35 grams. 143.35 grams of AgCl in a mole of AgCl. And then we'll go back to the balanced reaction to find a mole ratio. So we want the moles of AgCl to cancel. We want to solve for the moles of substance B, which is the excess remaining, which is AgNO3. So going back to the balanced reaction, for every 2 moles of AgNO3 that reacts, 2 moles of AgCl form. So we've got a 2-to-2 ratio. And now we want to know in 1 mole of this new substance B, AgNO3, how many grams are there? There's 169.9 grams of AgNO3 in a mole of AgNO3. So that the grams cancel, the moles of A cancel, the moles of B cancel, and we end up with grams of the excess. This is how much got used up in the reaction. So when we find the product of the numerator divided by the product of the denominator, we end up with a calculator number equal to 0.280895. Reported to 3 sig figs, it's 0.281 grams of AgNO3. So that's how much got used up or reacted or got used up in the reaction. Okay, that's how much got used up in the reaction. But we want to take the difference and we want to know how much excess remains. Well, going back to the question, we know that excess is AgNO3, right? So how much did we start with to begin with? So AgNO3 is silver nitrate. We started with 4.25 grams. So 4.25 grams of AgNO3. We're going to subtract it from what got used up, which is 0.281 grams of AgNO3. And the difference is 3.97 grams of AgNO3 remain. So that's how much excess remains.